Hello, it's Stat 134, Lecture 35. Last time, seems like a long time ago, we covered Section 6.2, Conditional Expectation, the discrete case. We learned that the conditional expectation is a function of x, what you're conditioning on, and you're essentially weighting all of the values of y by its conditional probability. And the conditional expectation is a random variable, so you can take its expectation, and that is the expectation of y, and that's called the law of iterated expectations. We then started section 6.3, conditional probability in the continuous case. We saw the definition for conditional density, which is a ratio of the joint density and the marginal density. We have this nice picture here seeing that the conditional density is a slice of the joint density through x equals x. And if you want to find the probability that y is in dy, given that x is x, you would take the value for your conditional density at y and multiply that by dy to give you that area actually shown in the picture. If you want the probability that y is dy, not conditioned on x is x, you would basically average over all of these slices for x in x, and that's called the integral conditioning formula. So today we're going to go over student explanations from the concept test that we did last Wednesday, and then we're going to discuss section 6.3. We're going to finish 6.3, discussing Bayesian statistics, the posterior density, and conjugate pairs, in particular beta binomial and gamma Poisson. So I asked you guys to get your head back into the concept test that we did last time. Let n have a Poisson mu distribution. Suppose that given n is n, random variable x follows a binomial NP distribution. The expectation of x is. So there are essentially two main ways to do this that you guys found. One is just using the definition. So the conditional expectation is a function of n, and it is NP since the x given n is n, that conditional distribution is binomial, and so its expectation is NP. So the expectation of that function, the way you find the expectation of a function, is you sum over all the values of n, and then you're weighing that function g of n by the probability that n is n for all the different values of n. So I use here the probability distribution for Poisson, and so g of n is np, so I pull out a p, and the n in the numerator cancels one of the n's in the denominator. And so then I can pull out one of the powers of mu, so I get mu p equals to a sum, and that sum is 1 since it's the probability distribution of Poisson, and so we just get mu p. A shorter way to do it is just to recognize that that the expectation of x capital N is capital NP. And so taking the expectation of that, the p is a constant, pulls out, and the expectation of n is mu, so we get mu p. So now moving on to section 6.3. We review the beta distribution. So remember that x is beta rs. If we have the following density for p between 0 and 1, so the variable part is p to the r minus 1, 1 minus p to the s minus 1, and the gamma function, gamma of r, is r minus 1 factorial. So, so for example, if your density is proportional to 1, then we know that x is beta 1, 1. If the density is proportional to p, then x is, because that's the variable part of a beta 2, 1. And if it's proportional to p1 minus p, x is necessarily beta 2, 2. So let's just remind ourselves what Bayesian statistics is about. So imagine that you have a probability p coin. Instead of thinking of p as a fixed constant like we do in frequentist statistics, we think of p as having a distribution that can change as we get more information about it. So we start off often having no knowledge of what p is. So we say that we give p a flat prior, basically saying that p has distribution uniform 0, 1. I made the random variable for px because capital P is used for probability, and I didn't want to use the Greek letter pi like your book does, so I just used x. Now, allowing our parameter p to have a distribution is called Bayesian statistics. Here's a picture of a flat prior. We did this last time. If you want to compute the probability that we get heads, then we would use the integral conditioning formula. So we're conditioning on all the different values p can take between 0 and 1. We get that probability is a half. So knowing about conditional densities allows us to compute the posterior distribution, where we update the distribution of p given that I1 is 1. So remember that the posterior is the likelihood times prior, and so the posterior is a constant times the likelihood times prior. The likelihood is p, and the prior is 1. So our posterior is necessarily beta 2, 1. If you wanted to find c, it would be gamma 3 over gamma 2, gamma 1, which is 2. So the posterior is actually 2p. And I graph that here so you can see that now the chance of getting I2 to be 1, given that I1 is 1, is going to be greater than a half. In fact, it's just the area. I mean, you can integrate this and just see what it is, right? You're integrating. But anyway, okay, so we're going to actually, never mind that comment, we're going to compute it right now. So let's find the probability that I2 is 1 given that I1 is 1. So we're going to use our integral conditioning formula. But first we're going to use Bayes' rule, and then we're going to condition. So now when we condition on x is p, the numerator factors, so we just get p squared dp, and in the bottom we get p dp. And when we integrate this, we just see that we get 2/3, which is greater than a half as we expected. So we can see that I1 and I2 are in fact not independent, since the probability that I1 is 1 times the probability that I2 is 1 would be a quarter. And the probability that I1 is 1 and I2 is 1 is 2/3 times 1/3 is a third. So those are not equal. So I had you guys do a similar problem on your own, and you guys did great at this. I don't really feel I have anything here to go over. It's just more of the same. And then we did a concept test, further building on this problem. So let A and B be events and let Y be a random variable uniformly distributed on 0, 1. Suppose that conditional on Y is P. A and B are independent, each with probability P. The conditional density of Y, given that A occurs and B doesn't, is, so it turns out to be beta 2, 2. And what we're looking for here is the posterior density of Y given A, B complement. We know that that's proportional to the likelihood times the prior. So it's a constant times, so the likelihood, you just basically change the order of what you're conditioning on. So it's A, B complement given Y is P, and the prior is just 1. So then because we're conditioning on Y is P, it factors, and so we get a constant P, 1 minus P, so we know it's beta 2, 2. And the next problem was very similar. It's just that now the posterior was a constant times P squared, so we knew that the posterior was beta 3, 1. And then we finally discussed conjugate priors. So when the prior and the posterior belong to the same family, we say that the prior and the likelihood are conjugate. Okay? So for example, what we'll see here is that beta and binomial are conjugate. And so we actually did this example back in lecture 29, so I'm not going to go over it again here. The binomial for likelihood and the beta for prior is a conjugate pair, since the posterior turns out to be beta. So then we finished with an example where I have 5 Poisson thetas, IID, and for unknown theta, but we're going to assume that theta is given by a gamma distribution with R and lambda known, and this is what Bayesian statistics does, and we want to find the posterior distribution. So first we need to write down what the likelihood is. I wrote the likelihood using F, even though Poisson is a discrete random variable. I should have used P, but I just get lazy. So you can write down what the likelihood is here, and then what we have here is this is the likelihood that I'm circling right now. So that's the likelihood, and this is the prior, just given by gamma. And so when you combine them, you can see you get something gamma. So the Poisson for likelihood and the gamma for prior is a conjugate pair, since the posterior is gamma. Okay, great day. I will see you on Friday.